Hello, everyone. In this talk, I'm going to talk about improved multipath streaming algorithms for submodular maximization with Matroid constraints. This is a joint work with Chen-Chung Huang, who is at ENS in Paris, and my supervisor, Justin Ward, in Queen Mary. So I'm going to first start by defining what submodular functions are. I assume most of you already are familiar with those, so I'll be brief. So a set function f is submodular if given two sets x and y and an element e not in y, the set x being including in y, the marginal gain of e with respect to x is greater than the marginal of contribution of e with respect to y. This is a notion that is commonly used, for example, in economics to define the utility of the customer. When I say that the function f is monotone, I mean that given two sets x and y, x being including in y, the value of the set x is less than the value of the set y. Additionally, the function is positive if given a set x, the value of x is greater than 0. So two examples of such function can be found, for example, when designing a network and understanding, for example, its robustness. An example of a non-monotone submodular function is, for example, the cut function. So given a graph G, I partition the graph into two parts, and my function, my submodular function, would be the number of edges going through this partition. So in this example, the value of the cut here would be 6. And you can see that if I'm picking another element and putting it in my partition, the red part, then the value of the cut becomes decreases. Now related to machine learning, submodular function have gained interest. So when in a document summarization task, the goal is to produce a summary that contains sufficient information from the document. So for example, you would try to summarize, take snapshots of some videos that would summarize the video, or in this example, you have a pile of documents, let's say a research article, and you want to select sentences or word that summarizes the research paper that you were reading. This is typically a setting where the set function is monotone, because the more sentences you add to your summary, the more information the summary will become, although the summary might not be more readable. Additionally, but on the other hand, machine learning has, in machine learning application, the data set is often huge. So most of the algorithms that were designed to study submodular functions become impractical because they assume access to the entire data set at all time. So submodular functions are now studied in more diverse settings, such that the streaming setting, which I'm going to talk about. So, oops, sorry. Yeah, so what is the goal? So the goal is to maximize this function f, and I have an independent system, which is a constraint on the set that I'm allowed to return. To maximize this function f, I'm given an upper bound k on the maximum size of the solution, as well as two oracles, one to query the objective function, and one to check whether the set is actually part of the allowed set. So the independent system is denoted by this calligraph I. The benchmark when studying such problem is when the independent system is actually a cardinality constraint. So in this setting, the independent system is actually all sets that have size less than k. The independent system can also be a matroid. So in this setting, you would like to have k element, but each, for example, of have contained are in different parts. You can think about like partition matroid. And the constraints that I will also talk about is P Matroid. And so I've written here the definition of a P Matroid, but what you can think about is about matchings. A matching is actually a two matroid, and this is fairly easy to see if you could. So let's say I'm given a graph G, and for each edge in my, so the calligraph N will be, the ground set will be all edges in my graph. And for each vertex of my graph, I will be defining a matroid. For each of these small matroid, the ground set will be the edges that are incident to the vertex. And the independent system of each of these small matroid will be the set of edges of cardinality 1. So just one edge going out of the vertex. And since an edge has only two endpoints, it is actually a two matroid. What is the setting that we're considering? So since I want an algorithm that doesn't require an access to the entire ground set, we're considering the streaming setting where informations arrive on the fly. So in this example, it can be the documents that you're reading. So whenever you see a sentence or a word, without having to look at everything next, you would either try to select it and put it in some memory of size polylog k, or discard this element forever. Elements in your memory can be either part of your final summary or can be discarded later. Note that I have a limited memory. The deletion of these elements is forever. And I don't assume any distribution on the stream. So the order of the stream can be adversarial. As we'll see, to design fast or to design good, efficient algorithm in such a setting, variation of local search and greedy algorithms are often performed. So what are the known results in this setting? So let's start first with the benchmark, which is the setting where most of the results are known. We know that there is a 1 minus 1 over E approximation, which can be done in actually 1 over epsilon passes. This result is fairly recent, and it's actually hard. So if you want to improve upon this 1 minus 1 over E, you need to make an exponential number of queries to your objective function. And as you decrease the number of passes, the best approximation ratio that you're able to get also decreases. So we know that there is a 1/2 algorithm in the single pass setting, which is actually tight. Turning to the single matroid constraint, we also know that there is a 1 minus 1 over E approximation, but the number of passes now becomes dependent on N. To get in 1 over epsilon passes, we're able to get a 1/2 approximation, but the single pass, in a single pass setting, we're only able to do a 1/4 approximation. And it is actually an open question to improve upon this 1/4 and to get a 1/2. Finally, regarding the P Matroid constraint, pretty much nothing is known, not nothing, but so there is a bit of a room to improve this 1 over p plus 1, which we do in p over epsilon times log square n, let's say, passes. So we don't know whether before our work there were no algorithm that would achieve this 1 over p plus 1 in a number of passes that is independent on n. And in a single pass, we can achieve a 1 over 4p. And again, since there is no hardness result related to there is no hardness result that extend to I mean, all hardness results for the offline setting are also hardness result for the single pass setting. But we don't have any specific result for the single pass setting. So we don't know what the correct answer is. So our contribution is is to get this 1 over p plus 1 in p over epsilon passes. And here is a table of the result that we get. I haven't discussed non-monotone submodular functions, but I invite you to pause the video here and to check the tables. Note that there are blank cells for the multipass setting for non-monotone submodular function. And it's actually because there are not results that are specific to the single pass setting. So the table was a bit too big. Anyway, so here's what we get. So we get a 1 over p plus 1 approximation algorithm for P Matrix constraints, processing the stream p over epsilon times. And from this result, we directly get a 1/2 approximation in 1 over epsilon passes, which we already knew. For some constraints that falls between Matroid and P Matroid, such as intersection of P Matroid, rank P archograph B matching, we remove a log P cubed log P dependence, and our algorithm is actually space optimal, storing exactly k elements. For a non-monotone submodular function, we get a 1 over p plus 1 plus gamma off approximation algorithm in the same number of passes. This gamma off parameter is the approximation of the best offline algorithm for the same problem. In the non-monotone case, the space complexity is clearly not tight, and yeah, there's definitely room to improve upon in terms of the space memory, as well as for the hardness, the approximation guarantee. All right, so how do we proceed to get those results? We actually use a streaming local search algorithm that was introduced by Chekuri, Gupta, and Kanrud. And I'm going to discuss mostly the Matroid case, but those results extend to the P Matroid case. So you might be already familiar with local search. So basically, when you have a local search, you have an element that arrives, and when you check whether the element is valuable enough, such that if you add this element in your current solution, this yields some improvement. So in the matrix setting, you would check whether the marginal contribution of your element E with respect to S is actually worth 1 plus beta times the some elements in your current solution. And this element is the elements that you would remove, so you want to maintain feasibility. So note that this WE prime S is not the marginal contribution of E prime with respect to S, but it's actually an upper bound on its actual contribution. And this is necessary because we are looking at the problem in the single pass streaming setting or multi-pass streaming setting. And first of all, a careful analysis of their algorithm actually shows that the following bound. So f of opt is less than 2 plus beta f of s tilde, where s tilde is our final solution, plus 1 over beta times the f of s tilde minus f of S init, where S init is the solution that we started with. So let me explain to you what those two parameters are. So what is highlighted in red is actually a part that you can't remove, because it's actually what you get from running this procedure in an offline setting. So in an offline setting, you would just check, have a solution, and do exchanges until you reach some local optimum. And you get this 2 plus beta approximation. On the other hand, since we're now in the streaming setting, there are elements you need to understand how much you lose by having elements in your solution at some point and later discard them. So you want to understand the weights of the loss that you want to upper bound the loss of the accepted and then rejected elements. And what you can show is that this loss is actually 1 over beta times the value of your final solution minus the value of the solution you started with. And this is what you can improve upon. So if you knew, for example, that just in a path your solution doesn't change, then this red side becomes 0 and you have a 2 plus beta approximation. All right. So what do we show? What do we use? Is that we use this result and actually run this procedure several times to show a fast convergence with a good approximation guarantee. So whereas we could set the beta to be the same, we actually change the beta on each pass to get an increase, to get a fast decrease, so an improved approximability. So yeah, so we just run this procedure, change the beta I, and use as our starting solution the solution that we ended up with in the previous pass. So how does it change with respect to the previous one? So there was a result from Chakrabarty and Kale where they get those results for example, P intersection of P Matroid. But what they actually do is that they only set the parameters so that they have some convergence is reached at the end. So they set the beta to be always the same, and they show that using the tuning of the parameter, there is some convergence, but their algorithm is not oblivious to the choice of epsilon. So what we use is that we use this ratio delta in our proof. That is the ratio between the value of the starting solution divided by the value of our final solution. And what does it measure? Well, if delta is small, then our one pass does make a lot of progress. So since we knew the approximation ratio of the previous pass, then our solution can only be better. However, if delta is large, so the one pass doesn't make a lot of progress, then we are also in a good shape because the value of the rejected, accepted, and then rejected elements is bounded by the quantity you see here. So this gives us enough room to update beta and to have a fast convergence. So we balance these two effects and we set beta smaller in each subsequent pass to obtain better guarantee. So this is in fact really simple, but it shows, so it's also what we're seeking. So this is the result that we get. We get that for an arbitrary P Matroid and a monotone function f, there is a polynomial sum algorithm that outputs a solution that is a P+1 approximation, and we only process P over epsilon times. In particular, for a single Matroid, setting the beta I being 1 over I, we get a 2 plus epsilon approximation in 2 over epsilon passes. What is also great about this algorithm is that our analysis is only in the worst case scenario. So what we can actually compute is this ratio delta. And so what we could do practically is updating those beta. So computing those beta with respect to the ratio delta that we get. Let me use the remaining minutes to discuss the non-monotonicity case. And the main issue is that, yeah, we no longer have the monotonicity, but what we can use is a monotonicity-like argument where we use this ninth theorem by Borbinder et al. And if we can upper bound the probability of an element to be in the set, then we can use some monotonicity-like argument. So what Chakrabarty and Kale, Chakuri, Gupta, and Kendra did is they introduced this notion of buffer when you process an element and it is good, you add it to a buffer of size polylog k, and once this buffer is full, you add it to your current solution. At the end of the stream, you have two solutions. The one that is the local search, but you also need to post-process the buffer because there might be elements of in up that are still in the buffer. But actually, the non-monotonicity case reduces to the monotone case in that the solution, the local search solution, is still maintained throughout the stream. So we can use the same type of argument to have a decrease in the local solution so we can use the analysis of the non-monotone case actually reduced to the monotone case because the solution that is maintained throughout the stream also has the same property. So we don't need much. The only downside is that the buffer size is actually big because we need to limit the probability of an element to be in our final solution. So yeah, our algorithm is clearly not space optimal compared to the monotone case. So for this is the result that we get for an arbitrary P Matroid and the submodular function f. There is a randomized polytime algorithm with total memory O of P cubed, yeah, the following quantity, and we have a P plus 1 plus gamma of parameter, a P plus 1 plus gamma of approximation, where, as I said, gamma of is the best offline approximation algorithm for the same problem. It's the ratio of the best offline algorithm for the same problem. So yeah, one more minute. In terms of open questions, of course, there is room to improve upon the Matroid case. Get a 1/2 in a single pass. This is still open, and that would rule out our algorithm. Although it is not clear that you can achieve a 1/2 using K memory. So maybe a 1/4 approximation is tight if you're only allowed to store K elements. But this is like a lower bound, some open questions that also needs to be tackled. And finally, the last question is to have some kind of framework that would turn any kind of streaming or local search like streaming algorithm to be multi-path streaming algorithm. So thank you all for your attention. Have a nice conference, and I'll be happy to answer questions either by email or in the chat. Feel free to reach me. Bye-bye.